Oh my goodness, here we are. Convert the following to polar form. We pick up from yesterday. Sorry for those of you who are lost, who don't know what's going on right now because you missed yesterday. We feel bad for you. Let us first think about the equations that are drawn. We have x is equal to 2y. What does that graph look like? Looks like a line. If you divide both sides by 2, you got y is equal to 1 half x. Very good. And so as you consider that, you understand that that equation y equals 1 half x is a line with a slope of 1 half that goes through the origin, correct? Now, I want you to think about that because that's going to change the way that we shape this graph. But as we think about this problem, I should say, if that's what it looks like, if I pick a point on here and I pick a point over there, are the r values or the distance from the center, are they the same or different? They're different. Both the theta values. Same theta values, right? Like here, theta would be like, I don't know, like 30 degrees. And here, theta is still 30 degrees, just the r value is negative, right? So would you agree that theta is the same all the time? And it doesn't even matter what r is, does it? So I'm going to convert this to polar form. For x, I'm going to place r cosine of theta. And for y, I'm going to place r sine of theta. Now, what I'd like to do is I'd like to solve for this in terms of r or in terms of theta. I'm going to divide both sides by r, and I get cosine of theta is equal to 2 sine of theta. Are y'all okay with that? Now I'm going to do something crazy. I'm going to divide both sides by cosine. What do I get? I get 1 is equal to 2 tangent of theta. Whoa. Look at the r value is gone entirely, isn't it? So we said it doesn't really matter what r is. What matters what theta is. Could I solve for theta? How would you solve for theta? Once I get 1 half is equal to tangent of theta, I inverse tangent. Well, where is tangent positive? Which quadrants? They're in the first and third. Isn't that where the line is drawn? So I inverse tangent. I'm going to work in radians because in polar form we work in radians. So I go to mode. I go down to radians, enter, and I do tangent inverse of 0.5, and I get 0.46. So that means that theta is equal to 0.46. So your equations for polar form need to have r or theta in them, or maybe even both. But because in this one you said it doesn't matter what r is, all that matters is what theta is, this is what we get. You good to go? That's your final answer. R or theta, or maybe both. This one, what graph does that make? A circle with a radius of 5. Everybody agreed? Think of a circle with a radius of 5. I want you guys all to think about that. The radius is always 5. Agreed? Does it matter what theta is? If theta was, say, 3 pi or pi over 2, is the radius value still 5? Say that the theta value was pi. Is the r value still 5? Say theta was 3 pi over 2. Is the r value still 5? So it doesn't matter at all what theta is, does it? So it's opposite of this situation. Here, all that mattered is what theta was. R did not matter. In this one, r does matter. Theta doesn't. So that's going to impact our answer. We've put in r cosine of theta for x. R sine of theta for y. And I get r squared cosine squared of theta plus r squared sine squared of theta is equal to 25. Sorry, I keep on writing 5. because I ate a bowl of stupid. All right. Now what do I do? So Maya sees that if I factor out the r squared, I have cosine squared plus sine squared of theta. And then I have equal to 25. Maya understood that because the capital of the United States is Washington, D.C., we also know that sine squared plus cosine squared is 1. I can't get you to recognize that. That has to be something that happens for you, folks. I wish I could just tell you that that's always going to be the case. You have to be able to look for that. So we get r squared is 25. So r is 5. Sure. And then when I tell you that 9x squared plus 4y squared is equal to 36, will you be able to tell me what r is equal to? No. Nope. But it's a good way to verify your answer. But you should be able to show me how you get there. Okay? So you can see how we get there. Hey, what I'm going to do is I'm going to take my calculator out. I'm going to go into y equals. And I'm going to press mode actually first. If you look down here, we're used to sitting in function mode, right? Can you graph a circle on your calculator? We can't because it's not a function. It doesn't pass a vertical line test, does it? But all of a sudden we go down here and we switch to, instead of function mode, we've switched to polar mode. And watch what happens. We press y equals and it says r. It's kind of cool, huh? I press r equals 5. Standard viewing window where we get that rectangular form. And now I'm going to zoom as a square so it balances it out. Did you get a circle? You sure did. You see, polar form allows you to graph things that are not normally functions in rectangular form, which is pretty cool. Allows us to make all sorts of unique graphs. Watch this one. That was kind of cool, wasn't it? In fact, if I change some things here, which seems like it'd be kind of difficult to do, but if I just change something here, I'm going to get more of that graph. That's pretty cool, huh? You can see the possibilities are really endless in the types of shapes that we're able to get, aren't we? So polar form is very powerful. It's used, especially as you get into Calculus 2, Calculus 3. It's good stuff. Let's look at our last one. X equals -2. What does that look like? It's a line. What kind of line? Vertical line. And you all know that if I draw a vertical line through x equals -2, here I have it. I want you to now think about the r and theta values. Suppose I pick a point here. And suppose I pick a point down here. The r and theta values, are they the same or are they different? Would you agree that they're different? Do the r or the theta values ever stay the same? No, they're always changing, aren't they? So in these situations, you saw that r went away. Here you saw that theta went away. Here it looks like r and theta are going to be related and stay together. So we're going to switch that x to r cosine of theta is equal to -2. And usually with parametric or polar equations, you solve for r. I divide by cosine of theta. And when I do, I get r is equal to -2 cosine of theta. Whoop. -2 divided by cosine of theta. You guys all know what 1 over cosine is because you all take college trigonometry. What is it? 1 over cosine is the same as what? Secant. Either one I would accept on the test. Mathematicians like to write that secant one. But your calculator doesn't have a secant button. So suppose I go in here and I go -2 divided by cosine of theta. And I press graph. Get a vertical line. That may not seem like a big deal to you, but if you were to go back into your rectangular form, your y equals, and try to graph a line that's vertical, you wouldn't be able to do it. I mean, because is that a function? No, it doesn't pass the vertical line test. It fails. So you can see the different shapes you're able to generate, which is pretty cool. So anyway, that's the first half of our lesson. Minimum. Parametric equations, really, they're equations who are dependent on a shared parameter or variable. So I'm going to do a demonstration here as you guys write this down. So often time is that third variable. And we don't show it on the graph. You can see the graph over here, we're going to have x and we're going to have y. But we are going to generate enough values using a table. Instead of just two values for a table, we have three. We're going to say time is equal to -3, -2, -1, 0, 1, 2, 3, 4, 5, 6. And we're going to use some x values and y values. We have to be able to generate the x values and the y values. So the x value gets generated by plugging in t for this guy right here. So we square the -3, which is 9, and then we subtract 3 times -3, or add 9. So you get 9 plus 9 is 18. Then we plug in -2. -2 squared is 4. And it's going to be plus 6 is 10. -1 squared is 1. Minus -3 is 4. 0 squared minus 3 times 0 is 0. 1 squared is 1. Minus 3 is -2. Plug in the 2. 2 squared is 4. Minus 6 is -2. 3 squared is 9. Minus 9 is 0. 4 squared is 16. Minus 12 is 4. 5 squared is 25. Minus 15 is 10. And 6 squared is 36. Minus 18 is 18. Are we okay with those sets of values? How do we generate the y values? You take the t value and you subtract 1. So -3 minus 1 is -4. -2 minus 1 is -3. -1 minus 1 is -2. -1, 0, 1, 2, 3, 4, 5. So there's our setting, okay? Now, what we're going to do is we're going to take these points, we're going to plot them using x and y. So I'm going to make 5, 10, 15, 20. -5, 1, 2, 3, 4, 5. So I have 18, -4. I go over 18. I go down 4. I have 4, -2. 0, -1. -2, 0. -2, 1. 0, 2. 4, 3. 10, 4. 10, 4. 18, 5. And you get that kind of shape. How would you describe that shape? A horizontal parabola. Is a horizontal parabola a function for x and y? It is not. Okay, so we struggled to graph that on our normal calculator. But is it a parametric function? Well, sure. Okay, as you describe t in terms of x, or as x in terms of t and y in terms of t, then all of a sudden it produces values that we like. has that function notation, but it's not, in terms of x and y, we don't consider it a function. And we're able to graph that. In fact, you could check your graph if you just go into y equals, and you go into mode, instead of going to polar mode, you can go down to parametric mode. And as you look at the parametric equation in y equals, now you can enter these things. Look, I've got t squared minus 3t, and I got t minus 1. There it sits right there. And as I graph it, look at what I get. Hey, what happened to the bottom part? Why? Why is it not there? Why? This is the negative time portion. In fact, if you look at your window, it says the time starts at 0. When did we start the time? We started time at -3. When did we end the time? At 6. And we said the x-min was, say, -10, and the x-max was, say, 20. And the scale was every 5. And then for the y values, we went to -5 and to +5. And now when we look at the graph, now do we see the whole thing? But this is one of the cool aspects about parametric polar equations, is that you can start to control what parts of the value you see, or parts of the graph you see. Sam, I want you to pick two numbers that sit between -3 and 6. Two numbers that sit between -3 and 6. Okay, so if I go in here, I could say I want t to start at 1, I want to end at 2, and I'm going to check out the graph. It just shows the section that sits between 1 and 2. You have total control over what portions of the graph that you see. You can graph things that seemingly are not functions. I had a student one time say, well, Mr. Gens, I think this is pretty cool, and so I'm going to try to come up with a graph. And so he did this graph. Do you know what I'm drawing? Yeah. Came up with so he looked online and he saw, a symbol for like the Batman. I don't know what it looks. I don't know. I'm not very good. But whatever the Batman symbol is. So the bat symbol, he came into class and he punched it all into his calculator and he spit out the Batman equation. He pressed graph and it got the Batman function going. It's pretty cool. Took a long time. It was like 40 minutes in class. But it was neat. Could you generate tables on a test like this? Could you plot them and make a graph for me? How about the second part where it says write an equation for the parabola by eliminating the parameter? We said that the shared parameter was time. Now we want time to go away. Anybody know how I could take x is equal to t squared minus 3t and y is equal to t minus 1? Anybody know how I can get rid of t? Erase it. Okay, I like that idea. It's another option that would have more mathematical thought to it. Okay. What if I went like this? What if I said that y plus 1 was equal to t? What could I then do with y plus 1? Substitute it in for t. We call this eliminating the parameter. So we're going to get t to go away. So now I have x is equal to y plus 1 quantity squared minus 3 times y plus 1. Y plus 1 quantity squared. What do I get when I square y plus 1? Y squared plus 2y plus 1 minus 3y minus 3. So y squared minus y minus 2. Everybody agree that from the conic sections test that we just took that would be a horizontal parabola? A horizontal parabola. And that's what we graphed right up here. Not the bat symbol. Sorry, everybody. You're going to have to look deep into the internet to find that one. What do you think? Last example. Cross out number 3. Cross off number 4. We dump down into number 5. After this, we move on to sequences and series, which are super fun. More fun than parametric and polar, trust me. It says, find parametric equations for the line with the given properties. Slope of 4 passes through -2, 5. And so what we have here is if I said write an equation for that line, you would say y minus y1 is equal to m times x minus x1. Now, just to review, if we use those properties, we end up with y what? Y minus 5 is equal to? Great. That was back in 8th grade, right? Piece of cake upside down. Like, that was super easy. Yeah, you liked it. Okay, all of a sudden math got more confusing all of a sudden, right? So we've got that piece right there, but this is rectangular form. What we want is parametric form. So we want something that says x is equal to, and we want something that says y is equal to. And x in terms of time, y in terms of time. So sometimes you'll see parametric equations with x sub t and y sub t. That means that t is the variable that you're going to use. So how do we go about that? And I think it's best to just start with a table, just like we did before. Time, x, and y. Let's start by graphing this line. If we're going to start something, what time would you like to start at? 0. What point should we start at? For this line. 0, 0 is not a point on that line. Let's start at negative 2, 5. So everybody agree that as we generate the graph of this line, we would start at negative 2, positive 5? Everybody with me on that process so far? Let's now move to the next point on the graph. As I move to my next point, how many units of time should we have go by? Let's have 1 time go by. Now we're at time 1, okay? All right, so I got to move to my next point. So if I start at negative 2, 5, how do I move to the next point? Up 4 and over 1. Everybody agreed? So I'm going to go over 1, and I'm going to go up 4. And what's my new location? Negative 1, 9. Should we advance forward another spot? What time do you want to advance forward to now? Time 2. Oh, okay. So if I advance forward to another point, up 4 over 1, or over 1 and up 4. Where does that bring me to? So if I go to time 3, anybody know what I'm going to have for an x value? 1. And how about the y value? And if I go to a time of 4, what's going to be the x value? 2 and, oh, do you see a pattern developing? So x sub t, the function x in terms of t, as time goes up by 1, what happens to x? It goes up by 1 as well. So the slope for the x equation is 1. Now remember, as you think about the y-intercept, that's when x is 0, what's the y value? So this is going to be the x-intercept. When t is 0, what is x? Negative 2. Let's look at the y value. As t goes up by 1, what does y go up by? 4. Hey, when t is 0, what is y? Let's check to make sure it actually works. If we plug in 4 for t, what's 4 minus 2? Let's plug in 4 for t. What's 4 times 4? Plus 5. See how you get all the points? So this is an equation for a line in parametric form that satisfies a slope of 4 and passes through the point -2, 5. We're ready to start your assignment.